This is part 1 of Unit 4, Lesson 4, an introduction to related rates and related rates. This is one of my favorite topics. It puts together everything we've done so far in differential calculus and applies it to some situations that are related to physics. And we're also going to see some related to some other areas as well. So we're going to start by taking some things that we've always talked about and putting them in terms of calculus notation. So I'm going to do a couple with you, and then I'll have you guys do a couple, and same with writing the formulas and taking the derivatives with respect to time, which is the next part here in 5 through 14. So doing numbers 1 and 2, we're supposed to take the volume of a cylinder is increasing at a rate of 6 cubic feet per second and put that into a calculus notation. So what we want to notice is all of these related rates are derivatives with respect to time. So this will be dv dt, and since it's increasing, it'll be positive 6 cubic feet per second. Okay, now you want to notice the units. Units are going to become very important. Sometimes when you're reading a problem, you're not sure what rate you're given or what measurement. Look at the units. If it's cubic, it's going to be some sort of volume. If it's square, it's going to be an area or a surface area. If it's linear, it's going to be a distance, or if it's per time, it's going to be a change in position, so that is a velocity. So that can help you figure out where to substitute things and what types of formulas you need as well. So just keep that in mind. So number 2, the depth of water in a rectangular pool is, now this says decreasing this time, at a rate of 2 inches per hour. So the depth is h, so dh dt is going to equal negative 2 inches per hour. And it's going to be negative because of the decreasing. Okay, I'm going to pause the video. You guys go ahead and try the next 2 before you continue the video. Okay, there's the answers to numbers 3 and 4. Hopefully you got those right. And as always, if you did not, you can ask in class tomorrow. All right, now we're going to be given formulas, and we're to take the derivative with respect to time. And remember, when we're doing this, now these are not super involved, so it's easy to consider and figure out which variables change with respect to time, because we really only have the variables that we have, all of them will change with respect to time. So I'm going to do a couple here, and then again, you should pause the video and do the others on your own. So starting with number 5, we're given the area of a rectangle is, of course, area equals length times width. So if we take the derivative with respect to time, we're going to have dA dt will equal, now we have a product rule here, so make sure you do that correctly. So we're going to have L times dW dt plus W times dL dt. Okay, the next one is a circumference of a circle. Now remember that 2 pi is a constant. The only variable on the right-hand side is r. So dc dt will equal 2 pi dr dt. Okay, volume of a cube is V equals the side cubed. So dV dt will equal 3s squared ds dt, our old friend, the chain rule. Next, the lateral surface area of a cylinder, S equals 2 pi RH. And again, we have 2 variables on the right-hand side, so we're going to have to use the product rule. And you can, if you want, factor out the 2 pi. So we're going to, the lateral surface area rate of change, ds dt, is going to equal 2 pi times, and then we're going to have h dr dt plus r dh dt. And the order of the terms is not important there. So if you wrote dr dt times h, that is also correct. I'm going to do the next two, and then I'll leave the last four for you guys to do. Area of a circle. Again, pi is a constant, so dA dt is going to equal 2 pi r dr dt. And the last one, perimeter of a square is 4 times the length of the side. So the change in perimeter with respect to time is going to equal 4 times the change in the side length with respect to time. And again, pause the video here and do the last 4 and then check your answers. Okay, and there's numbers 11 through 14. Hopefully you got those correct. All right, now, that's how we are going to write our related rates. So let's talk about how we go about using these to solve related rate problems. So what we want to remember, and I've already talked about this on the first page, is if volume is changing with respect to time, then dV dt is the rate or how fast the volume is changing. Remember that if something is growing in size, it's a positive rate. If it's like draining, it's a negative rate. But things like person walking by a street lamp, the distance is decreasing if they're walking towards the street lamp, and if they're walking away from it, the distance is increasing. So if they're walking towards it, their rate of walking is going to be negative, and they're walking away from it, their rate of walking is going to be positive. So things to think about. So here's some pretty good guidelines to use. They pretty much work for every problem. Make a sketch. It is helpful to see it. It helps you put in perspective where all the variables are and label things that you have. Another thing to do is to write down. Now, I'm going to give you these in this packet, but you're going to have to get used to writing these down yourself. What do I know? Things like formulas. Do I know the formula for the surface area of a sphere or a cylinder? What's given? Am I given any rates? Am I given any values for side lengths or radius or something like that? And then always write down, what are you trying to find? What rate? Is it the rate of change of the sphere? Maybe it's the rate of change of the radius. So you want to make sure that you do that. And always make sure you use the chain rule and use implicit differentiation on both sides with respect to time. So after you do that, you want to substitute in all the values that you know, and you should be able to get the related rate that you're looking for. So don't do any substitution until the end. Okay, so let's go through a couple of examples here and see how we do. Suppose x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. So we are to find dy dt when x equals 3, given that dx dt is 2, and of course that is when x equals 3. So this one is just kind of like a baby step problem into it. So the first step we want to do is we want to take the derivative with respect to time. So we're going to do dy dt. That's going to be our first step. So we're going to have 2x dx dt minus 3 dx dt. Now the next thing you want to do, I can simplify this a little. Let's do that. That'll make our substitution step, which is next, a little easier. So we can factor out that dx dt. Then we're not substituting it all over the place. There we go. That looks a little nicer. So the next thing we want to do is we want to, so here we differentiated. That's supposed to be an A, not a D. Then we're going to substitute everything we know. All right, so what we know is we're trying to find dy dt, so we're not going to substitute anything in there. That's what we're trying to find. Dx dt we know is 2, and then we have 2 times, and x is 3. Okay? So we finally get that dy dt at x equal to 3 is, so we're going to have 6 minus 3 times 2 is 6. And it's positive, so it's growing. Okay, next example. This is a more typical example. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of disturbed water changing? So looking at our picture, we have where the pebble went in, and then we have a concentric circle, and then another one. So what we're looking for is if we know when r is equal to 4 feet, what is the area of that circle, that outer circle? So that's what we're trying to find. We know the formula for area of a circle is pi r squared. And what is given? Well, we're given that the change in the radius over time is increasing, so it'll be positive of 1 foot per second. And we also know we want to find this when r equals 4 feet. So what are we trying to find? We're trying to find the change in the area. Okay, so we're going to take our area formula, which is A equals pi r squared. We're going to differentiate it with respect to time on both sides. Okay, now we're going to substitute. So we want to find dA dt. That's going to stay. And we're going to substitute everything else. So 2 pi is 2 pi. R is 4 feet. And I always recommend putting the units in at this point because it'll help you get the correct units at the end. And then the rate of change of the radius is 1 foot per second. Okay, multiplying that out, we get that dA dt is equal to 8 pi, and so we have feet times feet, feet squared per second, which is what we would expect for rate of change of area. Area is square units, so we have square units. So that's our answer to example 2. I'll do one more, and then I'll stop this video, and I'll finish in the next video. So the next example says air is being pumped into a cylindrical balloon. So that means that the rates are getting larger at a rate of 800 cubic centimeters per minute. So this unit right here tells us that this is the dV dt. Because, I don't know why that line won't go there, because that is a cubic measurement. So it's got to be the change in the volume. How fast is the radius of the balloon changing? At the instant, the radius is 30 centimeters. So we need to know the formula for the volume of a sphere. So that is 4/3 pi r cubed. What is given is dV dt, and I know it's the volume change because of the units, is 800 cubic centimeters per minute. And I also know I want to find this out when r is 30 centimeters. You also want to make sure when you're writing these that all of your measurements are in the same units, because they might trip you up and you might have to change maybe from centimeters to meters or vice versa. So we are asked to find the rate of change. How fast is the radius of the balloon changing? So we're looking for dr dt. Okay, so our units should end up being centimeters per minute because radius is a linear concept. All right, so we're going to start with our equation, which is, I didn't draw a picture though. I like my pictures. So here's my sphere with a radius of r. There we go, much better. Okay, so we're going to start with V equals 4/3 pi r cubed. Now we're going to take the derivative with respect to time. So dV dt is going to equal 4 pi r squared times dr dt. Okay, so now we can substitute in everything that we have. So we know that the rate of change of the volume is 800 cubic centimeters per minute, and that's equal to 4 pi times 30 centimeters squared, and then we have times dr dt. So what we're going to do then is divide 800 cubic centimeters per minute by 900 pi. 900 times, here, let me just do a little quick math here, because I can divide out the 4s here into the 800. So I'm going to do that. So I'm going to have 200 cubic centimeters over 30 squared is 900 pi. And that's going to be centimeters squared. Okay, now if you notice that the hundreds will cancel, and the centimeters cubed will cancel with the centimeter, so I'm going to be left with centimeters per minute. So I'm going to be left with 2 over 9 pi centimeters per minute is going to be dr dt. And you really have to look at the problem. If it's not a calculator problem, just leave it like that. Don't go to the trouble to try to multiply pi out or anything. It's not really worth it. Okay, so I'm going to stop here for our first video, and we'll pick up with example 4 in the next video.